Thank you very much for, I cannot say the invitation because I'm the CEO of Norcell, so we organized together. But thank you for Sohan for all this idea of Norcell, because it's really an exciting idea and project that we go through together, changing all the time our mind, but still evolving towards something better. I'm sure about this, and I can feel it and I can see it. So today's contribution from my side is a project we have, a European Space Agency project, which has to do with development of an instrument. This instrument is going to be a very small instrument, which is it's a microfluidic instrument actually, which is going to be able to identify reactive oxygen species on planetary regoliths, soils, and ices. So if I go to the next, but it doesn't move. Let's do it from here. Yeah, I have to do it differently. This is the group of the people working in this project. The first line is my group. You see the second person is sitting close to us. The others are some students of mine. The second group is actually from Professor Georgiou. He is the initiator of this idea, actually, because he's done a lot of experiments in reactive oxygen species. He's a biochemist, and he worked also, and he tried with NASA as well to perform this task. Finally got funded by ESA. His group is these four girls on the right. And on the last line, you will see an SME company, a Greek SME company, which is helping us in developing this instrument, because they have a lot of assembly capabilities and microfabrication capabilities, also design as well. And on the right, bottom right, you will see Malgorzata Holinska, who is the project officer from ESA, and she is very involved and very supportive in this work we are doing. So what are reactive oxygen species? These are highly toxic substances. And just very quickly, a small list here is given. Hyperoxides in general, hydrogen 2, oxygen 2, free oxygen, negative or positive. You can find them, all of them absorbed as absorbed oxygen, or metal salts, like, for example, potassium oxide and sodium, and as ionic complexes with different metals. Then you have hydroxyl radicals, which we will explain later how this will be sensed with the instrument, because we do both. And then come perfluorates that recently were found on planet Mars, and they contribute in the same way to the toxicity of the soil. Now, how raw species are formed? You have heard a little bit in the previous talk about these processes. One of these processes is cosmic ray interaction with ices that you see on grains of interstellar grains. Or if you take minerals and you fracture them in small pieces, then you generate free bonds on their surfaces. And this, through this blue reaction, you see, I don't know if you see it, yeah, you see it. This one, you see how these are formed, and also OH, free radical of OH. Then there are penton reactions, like this kind of change of on iron mostly, and this happens on lunar and Martian dust. And finally, you can have also, this is mainly on Mars where you have carbon dioxide, scattering of CO2 on solid surfaces via charge transfer from the surfaces. I don't go too much in detail on those, but how this whole story started and why ROS. We go back to the Viking lander, in 1976 with the first experiment to identify life on Mars, and this was the gas exchange experiment. Where, very simply, what they did is to mix nutrient medium, which we usually put in our Petri dishes to grow cultures of bacteria, and they mix it with Martian soil. And from 1 cubic centimeter of Martian soil, they could produce oxygen gas, which was of an estimate, not estimate, measure amount of 770 nanomoles. This could be an indication of life on Mars, but they did additional experiments, like, for example, taking the soil, heating it up in 145 degrees, and in another experiment, 160 degrees, for 3 hours. With this, they were expecting that everything organic, life or organic, will be killed. And then they repeated the experiment. They cooled down the Martian soil, and then they just put it together with nutrient again, and they realized that still oxygen exists. So probably this is not life. That's why they will start thinking of other ways of producing oxygen, and these were the reactive oxygen species that came later on. There are several papers around this suggestion. Here you see some results from an experiment, and not our experiment, it's in the literature. You see the literature with green letters on the top of the figures. If you have a soil, in this case, they use the simulant of Martian soil, and you irradiate it with UV of about 20 hours. Then from the yellow line, the yellow curve, you get to the red one, and you measure a lot of charges created on the soil. So this means that by irradiating with UV the soils, you can create reactive oxygen species, which can remain really, even if you hit the sample. The right figure shows this. They were hitting the sample for 1 hour in 100 degrees, and then another hour in 200 degrees, and only then it started, reducing in concentration, which explains also the experiments that Viking did on Mars. For us, this was useful information because this means that very quickly, in a few hours, you can induce on any soil reactive oxygen species. That's why we thought about the OXR device, oxygen release device, and we thought that we can identify areas on Mars where life could exist, or has existed, and left some organic signatures. So the very basic idea behind it is just take some soil, then wet it. We spray with some water, or we put it inside water. And if oxygen is released, then regolith contains reactive oxygen species, which means no life there. We better leave this place and go somewhere else to look for life on Mars. But if there is no oxygen released, then we say that this is a good area to get a sample and bring it back to Earth, for example. Okay, so much more possibilities to get this job done, because, as we said, reactive oxygen species react totally with organics, and they break them, so you will not see signatures. Behind this instrument, all these reactions take place, and also different parts of the instrument are integrated in this scheme, but I don't want to make it complicated. I will make it very simple to you, and this is how it's going to work. This is the main reaction here. You have, for example, the soil, okay, irradiated with UV. In our case here, but on Mars or on Moon, you don't need to do it because it's naturally irradiated from the sun. just some more water on it. Then you take the solution that it's created, and this one contains OH and peroxides, hydrogen peroxides, and immediately you have some oxygen release as gas. This is the first measurement we do for oxygen release. Then we have two paths and two parts on the instrument itself. One part is to take this peroxide and put it through, make it flow through a manganese oxide, which is used as a catalyzer. And then this recombines, breaks and recombines to water and some second stage of oxygen release again. So we have this oxygen plus this oxygen coming out. And then the other part of the instrument takes again this solution, and then we use TPA. This is terephthalate, an organic plastic monomer, from which we make plastics. And this is very cheap also, and very stable in any conditions. So if we just put them together and they react, the solution, actually the original solution, contains already this TPA. So we don't need to do this mixing afterwards. So those two together, they combine and they make a fluorescence substance. And we measure this fluorescence, and I will tell you how. Now, here it is how. Actually, this is done already with a bigger instrument, but we can do the same with a miniaturized device that we are developing. We have already bought some filters and sensors, photosensors, and the concept behind it is that if red is the measurement, actually the fluorescence that is produced from TPA combined with hydroxyl, then if we take two measurements at the background and one measurement by irradiating it with this LED, UV LED at 310 nanometers, you have this emission at 420 nanometers. And then if you we just check the background as well, then we can have the estimation of the peak of this of the fluorescence, which means we can also quantitatively measure this. So this is the idea for OH measurement. And the gas oxygen measurement we do with existing OEM parts like this device here. The actual device is this one. This is just a bench top to make the connections to this because it's very small. It has an optical fiber that goes directly to this T junction. So through this, you have the flow of air or liquid. And with this light, this blue light that you see here, you have you have a small material, a tape with a special chemical that reacts with oxygen and quenches the light if you have oxygen in the fluid or the gas that comes through. So this is quantitatively measured. We did several experiments and it works fine. And now we are trying to integrate everything in one device. This is a larger device. This is about 10 by 10 centimeters. You can see very easily that it can be done very small. But the actual final device is going to be a microfluidic device. It could be of one use or multiple uses. We will see how we will develop it. We use 3D printing and electronic prototyping, and we integrate OEM devices. And some of these OEM devices are also built and they are patented from this company that we are working with. And I will show you what it is in the next slide. So we are TRL 3 at the moment. The whole chemistry, we know that it works. But as a device and as a concept, we are TRL 3, and we are going to go to TRL 4 to 5 with this project now. A later project, a continuation of this project, could make it very easily a flight instrument to go to Mars as well. So this is how we will integrate everything through these controllers, very, very small controllers. Integrated, all these three integrate to this small box, which is about the size of a 50-cent euro coin. And you have a power control, you have microprocessor unit with memories and all the controlling that you want, and IoT operation. And you can have an ultra resolution encoder in the cases you need to have some kinematics. This is called super modified, and all of it together costs about 100 euros. Now with the increased prices, in the past it was 70 euros. We have to build or to synthesize better our own materials to test the instrument. That's why our group's job is mostly this, although I work a lot with the instrument itself, because in the past I worked several years in microtechnologies and photonics. So I have a lot of integration in microfabrication, a lot of experience in integrating systems and MEMS and photonics and sensors. So this fits very well together with my geological background to build such instruments. So the natural materials we're testing are monomineralic powders. For example, we see the effect of each different mineral on oxygen production. Then we will use synthesized simulants. And we do the synthesis here, and we have to do it in a very special way. We cannot just buy anything because there is a lot of contamination and we don't know how they are synthesized. So we have to really build it, synthesize them ourselves. For example, oxygen contamination of the atmosphere is very common. That's why we have to build to synthesize everything under vacuum or special inert gases. We have also commercial simulants to test with. We have bought several lunar meteorites that we are going to grind and experiment on those. Of course, only Mars materials we don't have, but we will just use the simulants we produce. So the operation requirements are that the device should run under vacuum or variable pressure and different atmosphere devices that chambers that we can put different gas mixtures there to simulate any kind of atmosphere and how this device would work anywhere. The device should run under microgravity. So this is a solution that can be done easily if we use an all fluidic device. So the whole system is really filled with the fluid we want, this TPA water solution, and no gas bubbles. And if we have a little bit of higher pressures, then we can, depending on the temperatures, we can keep it running under control without bubbling of the oxygen. It should remain dissolved. And of course, the system should have a very precise temperature control because the oxygen sensor is very, very sensitive to temperature. With small changes, you have different readings. That's why it's self-regulating the system as long as you give it the temperature, and it does it automatically. Now, what we need is finally with this device is to estimate also the oxygen release from Martian soil, but not only from Martian soil. Our main focus at the moment is lunar soils and regolith. So if we just we have information about Mars with the Viking experiments. So we know that 1 cubic centimeter of Martian soil produces 770 nanomoles of oxygen. Okay, if we just say that we start scanning and sampling the very top layer, 1 centimeter or even less of the lunar soil, you have a flat area, and like you do with agriculture, crops, the same way you go with a robot up and down, and scan it and process it and leave it behind. The material that you get, you leave it behind. You don't carry anything, you don't mix too much, and you just do it on 1 hectare of Martian soil, the very top. You have about 100 processed, you have processed about 150,000 kilograms, which releases 77 moles of oxygen. And if you just convert this one to oxygen gas, You have about 1,725 liters of per hectare of other gases like nitrogen, for example. You make breathable air like we have here on Earth, which is about 8,000 liters. And this is what we need to breathe per day as a person if we don't do if we do moderate work, actually. Okay, this is a daily, as I said, air consumption of a person, also on the moon or on Mars, which means if we continuously go and process the same soil after we leave it periodically, after we leave it for some time, to reactivate from the UV radiation of the sun, then you have, like in agriculture, periodically processing of and use and extraction of oxygen from many hectares of area. A hectare is a little bit larger than a football stadium. So this is quite effective, I believe, and this brings us to this idea, finally, what we call it oxygen farming concept. And this is what I explained. You can have installations on the moon, for example, to periodically process lunar or Martian soil. Then you leave this area to regenerate from cosmic radiation and produce new reactive oxygen species. And then you go again and process it, and continuously you produce oxygen. This has minimal energy requirements. You need just a photo, how's that? I forgot. Photo cell.
Yeah,
But yeah, you don't need other kind of energies there. So it's very low in the requirements. And for the chemistry, you don't need any high temperatures. You don't need to heat your soils into very high temperatures to produce this. You just wait that the sun does the job for you. So this is our device. Thank you very much for this opportunity to talk here, Sohan especially.